Hi, this paper will be discussing SignNet, which is a sign generation model. Given text, the goal is to convert to sign language. Yeah, the authors of this paper are Ananthanarayana at SUNY, Lipisha Chaudhary at the University at Buffalo, and myself, Ifeoma Nwogu, also at the University at Buffalo. So really the motivation for this work is the fact that now we have these personal assistants, Alexa, Siri, Bixby, and many others, and these are voice-controlled systems. So for those who are deaf and hard of hearing, then it's almost impossible to have access to these kinds of systems. And so if possible, could we have a two-way sign language controlled system similar to these personal assistants? Now, translating sign to text is already a research problem that's actively worked upon. But the other way, translating text to sign, which is really spoken word to text to sign, is a more challenging AI problem. And that's what we focus on in this paper. So the main contribution of this work is really investigating the presence of different aggregated losses, including a novel similarity metric-based loss for improving text-to-sign language generation. Yes, so why is this a difficult problem? Sign language has to do with hands, which is called manuals, and non-manuals, which is facial expressions, gaze, torso, movements, etc. Oftentimes, when we think of sign language, we only think of the signs, the symbols made with hands, but there's also non-manuals. But even that, hands are in 3D space, it's a visual temporal process as opposed to speech, which is linear, it's ordered, and yeah, so it's linear and ordered, almost like a one-dimensional process as opposed to three-dimensional. And so the goal is to take text, translate to this three-dimensional visual construct. Sign language has different grammars, it has different word orderings from its spoken counterparts. And so we really have to learn that mapping. Now, gloss is a transcribed form of sign language, which involves written words, symbols, and the ways to produce a sign. And so you look at something like this complicated writing, and the interpretation in the spoken version would be, yesterday I worked, a stranger brushed past me. So that just gives you a sense of the complexity of gloss to sign. These are just some related works that can be seen in the paper. This is an example of our model or a schematic showing the encoder-decoder transformer-based model that we use. So here the input is text, or it could be gloss. This goes through an encoder, a transformer-based encoder, but it has to be decoded to what we call poles, three-dimensional skeletal poles. And so essentially, this is a sequence-to-sequence model, but the nature of the inputs and outputs are different. And also, so here we see the kinds of losses that are back propagated through the system. And this is what part of what we're investigating in this work. Right, okay, so this is just to introduce the metric embedding loss, in which case we have a baseline, we have the truth, the actual sign, the ground truth. We have a false sign, which is another sign in the batch. And so here we take our prediction, the ground truth, our prediction, and another sign in the same batch on the assumption that two signs in the same batch, two phrases will not be the same, or will be close, but not the same. We want the distance between BT and BS to be small, and that makes the that makes the network, that makes it hard for, it forces it to work hard to learn the difference between the ground truth and the prediction versus any other science phrase and the prediction. These are some examples where this is what just the problem as it's posed, this is what the solution would look like. And the two losses we investigate here are the traditional regression loss, mapping two output sequences, and the sign similarity loss, as shown on the previous page. This here. And the total aggregated loss is the combination of the two losses. The lambdas we have here are learned through a grid search. In the paper, we provide information on the ablation study. Again, this is a model we just went through, and I wanted us to see this in comparison with the back translation. So for evaluation, we do a back translation where we have a symmetrical model, but instead, pose is input and it's decoded into text. And we take the predicted pose from the previous model, run it through this model, encoder, decoder, decode into text, and then run our metrics on the translated text. Yes, these are the losses for the evaluation model. This is the data set. It's the Phoenix data set by Kloss et al. These are evaluation metrics. We have blue score, and we use dynamic time warping as a stopping criterion. These are some of our example results. This is just a very good example where the ground truth came out very similar to the predicted pose. In this case, you have the ground truth and the predicted, and we have the English translation so that folks who don't speak German can take a look at the difference, the similarity or differences in translation. We do an ablation study on, actually we compare with other models in the literature. And finally, we do an ablation study without the similarity loss. All of it pointing to the fact that SignNet with metric-based loss significantly outperforms the model without the loss. Thank you.